Welcome to Study Loop.
So we have a parallel plate capacitor with a 4 centimeter radius and a conduction current of 0.280 amperes. We want to know the displacement current density, the rate of change of the electric field, and the magnetic field at two separate radii away from the center. So for A, the first thing to realize is that actually the conduction current is equal to the displacement current in this particular situation. So that comes just directly from the definitions of those two quantities. Therefore, the displacement current density is the displacement current divided by the area in question, but that is just the conduction current divided by the area in question, which is IC over pi r squared, where r is the given radius. So this is just 0.280 amperes divided by pi times 0.04 meters squared. And that's 55.7 amperes per meter squared. 55.7 amperes per meter squared. So that takes care of A. What about B? So B asks for the rate of change of the electric field, but now that we know the displacement current density, we can use the formula for the displacement current. So the displacement current density, which is epsilon times dE dt. Now, in our case, our capacitor is filled with air, so epsilon is equal to epsilon naught. This is epsilon naught times dE dt because we have air. Therefore, we can just solve for dE dt. So dE dt is going to be JD divided by epsilon naught, which is the number we got from A for our displacement current density. That's 55.7 amperes per meter squared. And epsilon naught is a known constant, 8.85 times 10 to the minus 12 farads per meter. And if you calculate that, you should find that it is equal to 6.29 times 10 to the 12 volts per meter second. Okay. So that does it for the rate of change of the electric field. Now let's move on to the magnetic field. So finding the magnetic field is a bit trickier. So I'm going to start a new page here. So this is sort of a side view of the capacitor. So we're looking kind of down the barrel of it. This is the radius of our capacitor, which we know is 4.00 centimeters. Let me rewrite that, 4.00 centimeters. And we want to know what the magnetic field is, a distance r equals 2.00 centimeters. So this is, again, an application of Faraday's law. So this is an application of, B dot dl equals u naught I enclosed, so Faraday's law. As is always the case, this integral is going to simplify to just b times 2 pi r. But then what's I enclosed? So the whole point is that the current is this current is distributed across the entire surface of the plates of the capacitor. So the question is, what fraction of that current is just in this chunk? So that's I enclosed. I enclosed is what fraction of the current is just in that chunk. And the answer is actually given directly by the current density. So because there's a constant density, the amount of current in this chunk of the area is actually just going to be the ratio of the area of this red circle to the overall black circle. It's going to be the ratios of the areas. So what we're going to have is that I enclosed is pi r squared over pi capital R squared times the conduction current. So another way to see that is with the definition of the current density. So remember, the current density we had was the conduction current divided by the area. But this is constant, right? The density is constant. So this is also equal to the conduction current in some other part, right? So this is the first conduction current in the first area that's equal to the second conduction current in the second area. And then you put the area, just multiply both sides by the area, and you get this. Right, so that's another way to see that. So once you have this, we can do some cancellations. So there's going to be a few cancellations here. We're getting rid of these pi's, and we're getting rid of one factor of r. So what we're left with is b equals mu naught I c over 2 pi times r over big R squared. So that's the final formula for the magnetic field. And now we can put the numbers in. So mu naught is 4 pi times 10 to the minus 7 newtons per ampere squared. The conduction current was given to us. That's 2.80 amperes. And then we've got a 2 pi downstairs. Our R is 0.02 meters. And capital R is 0.04 meters squared. And if you calculate that, you should find that this is 7 times 10 to the minus 7 Teslas. So the tricky part is really this argument over here, figuring out the I enclosed, but again, the punchline was just that the current enclosed is the total current, the conduction current, but scaled appropriately, right? It's rescaled by what fraction of the area over here you actually have. Okay. And then for D, well, you can just put in the only number that's different is this one, right? Oh, shouldn't have erased that. The only number that's different is this one. So all we have to do actually is divide our answer from C by 2, right? It's the answer to C divided by 2 because all we're doing is dividing this number by 2, right? Instead of the radius being 0.02 meters, it's 0.01 meters. So therefore, we can actually quickly see that in this case, the answer is going to be 3.5 times 10 to the minus 7 Tesla. And that's the full solution to the problem.